Machine learning algorithms performance metrics metric-driven development lies at the heart of building effective machine learning systems. Whether classifying images, predicting stock prices, or recommending products, evaluating algorithmic performance ensures models meet desired outcomes. This article dives deep into the world of performance metrics, exploring their roles, nuances, and practical implications. Performance metrics provide objective criteria to assess, compare, and refine machine learning models. They quantify success, identify weaknesses, and guide decisions, from feature engineering to hyperparameter tuning. Understanding which metric suits your task is critical to avoiding misleading conclusions about model efficacy. Evaluating classification models. Classification tasks involve categorizing data into predefined classes, making accuracy a commonly used metric. Accuracy measures the ratio of correct predictions to total samples, offering intuitive insights. However, imbalanced datasets can skew results, leading to overly optimistic assessments of model quality. To address imbalance, metrics like precision, recall, and F1 score become essential. Precision evaluates the proportion of positive identifications that are actually correct, while recall quantifies the ability to capture all relevant instances. These metrics balance false positives and false negatives, ensuring fairer evaluations. Precision focuses on minimizing false positives, ideal for cases where incorrect identification has high costs, e.g., spam detection. Recall prioritizes capturing all relevant instances, vital in scenarios like disease diagnosis, where missing a case can be dangerous. The F1 score combines precision and recall into a single value via harmonic mean, providing a balanced assessment. It's particularly useful when dealing with skewed class distributions, as it avoids favoring either precision or recall excessively. Confusion matrices offer visual clarity, displaying true positives, true negatives, false positives, and false negatives in tabular form. Analyzing these values helps pinpoint patterns and errors, guiding targeted improvements. In multi-class classification problems, micro-dash, macro-dash, and weighted averaging methods adjust metrics to account for varying class sizes. Micro-averaging aggregates contributions from all classes, while macro-averaging treats each class equally regardless of sample size. Regression model assessment. Regression models predict continuous numerical outputs, necessitating distinct evaluation strategies. Mean absolute error, MAE, calculates average absolute differences between predicted and actual values, providing straightforward interpretability. Unlike percentage-based metrics, MAE remains consistent across scales. Mean squared error, MSE, squares residuals before averaging, amplifying larger discrepancies' impact. While sensitive to outliers, MSE encourages smoothness in predictions due to its mathematical properties. Root mean squared error, RMSE, normalizes MSE back to original units, facilitating direct comparisons with target variables. R-squared, R superscript 2, measures the proportion of variance explained by the model relative to baseline benchmarks. Values closer to 1 indicate stronger fit, though R superscript 2 alone cannot confirm causality or model validity. Adjusted R superscript 2 penalizes unnecessary complexity, discouraging overfitting through additional features. For time-sensitive forecasts, metrics like mean absolute percentage error, MAPE, express inaccuracies as percentages. However, MAPE struggles with zero or near-zero targets, causing infinite or highly variable results. Symmetric MAPE mitigates this issue by averaging absolute errors symmetrically. Custom loss functions often emerge in domain-specific applications, allowing developers to encode business priorities directly into evaluation frameworks. For example, financial risk modeling might prioritize minimizing extreme losses over general prediction accuracy. Interpreting probabilistic outputs beyond binary classifications, probabilistic models output confidence scores that require nuanced evaluation. Log loss penalizes confident wrong answers harshly compared to uncertain ones, encouraging calibrated probability estimates. It's widely used in competitions like Kaggle for ranking submissions objectively. Receiver Operating Characteristic, ROC, curves plot true positive rates against false positive rates across threshold variations. Area Under Curve, AUC, summarizes overall discriminative power, with higher values indicating better separation between classes. While AUC provides global insight, PR curves focus on precision recall dynamics, especially useful for rare event detection. They highlight how changing decision thresholds affects both metrics simultaneously, aiding fine-grained calibration efforts. Cross-validation becomes indispensable when validating these metrics. K-fold cross-validation partitions data iteratively, ensuring stable estimates despite limited training samples. Stratified sampling preserves class distribution during splits, preventing biased assessments. Handling imbalance and noise data imbalance poses significant challenges, distorting conventional metrics disproportionately. Techniques like SMOTE artificially oversample minority classes while preserving underlying structures, enabling better representation without biasing results. Noise introduces randomness that corrupts signal integrity, complicating evaluation processes. Robust error metrics like median absolute deviation, MAD, resist outlier influence better than standard deviations in noisy environments. Anomaly detection requires specialized approaches since traditional accuracy metrics fail dramatically. Isolation forests isolate anomalies efficiently by measuring path lengths in tree structures, a fundamentally different paradigm from conventional scoring mechanisms. Ensemble methods aggregate multiple weak learners' opinions to produce consensus judgments resistant to noise interference. Stacking combinations yield superior stability compared to standalone predictors, particularly under volatile conditions. Ethical considerations in metric selection. Metric choice carries ethical weight, influencing fairness and accountability dimensions. Overemphasis on accuracy may inadvertently perpetuate biases present within training data sources, leading to discriminatory outcomes downstream. Fairness-aware metrics incorporate demographic parity constraints explicitly, enforcing equal treatment standards irrespective of protected attributes. Disparate impact analysis identifies harmful disparities systematically across groups defined by gender, race, etc. Transparency demands interpretable architectures paired with explainable metrics rather than black box alternatives. LIME explains complex models locally by approximating them linearly near individual predictions, an approach compatible with various evaluation schemes. Accountability mandates traceable audit trails linking final decisions back to measurable inputs. Version control systems track metric changes over time, establishing clear lineage for regulatory compliance purposes. Real-world applications and case studies. Healthcare diagnostics exemplify the criticality of precise evaluation. Radiologists rely on sensitivity measurements above others because missing cancerous tumors risks patient lives far more than false alarms do. In contrast, credit card fraud detection prioritizes specificity to avoid blocking legitimate transactions unnecessarily. Manufacturing defect inspection benefits from combining multiple metrics strategically. High recall ensures no faulty items pass undetected, whereas moderate precision keeps rejection rates manageable for production lines. Balancing these factors determines operational efficiency levels directly. Social media moderation leverages nuanced scoring mechanisms. Content filtering platforms minimize harmful material exposure while safeguarding free expression rights, requiring careful calibration of precision/recall ratios according to platform policies. Climate change research employs novel metrics tailored specifically for environmental data sets. Cumulative distribution functions analyze frequency patterns instead of absolute values, revealing meaningful trends obscured otherwise. Trends shaping future evaluation frameworks. Explainable AI drives demand for interactive visualization tools integrating real-time metric updates alongside model predictions. Users can explore trade-offs visually before committing to deployment choices confidently. Differential privacy introduces noise intentionally during computations to protect private information. Evaluators must adapt existing metrics accordingly, accounting for deliberate obfuscation added mathematically controlled ways. Federated learning decentralizes computation geographically, challenging traditional aggregation methodologies entirely. New distributed evaluation protocols emerge naturally, aligning better with infrastructure realities. Quantum computing promises exponential speedups theoretically, although current implementations remain experimental. Early adopters experiment cautiously with prototype quantum algorithms, developing hybrid classical/quantum evaluation pipelines incrementally. Conclusion: selecting appropriate performance metrics is foundational to successful machine learning projects. Whether optimizing for cost-effectiveness, safety margins, or social equity considerations, thoughtful measurement strategies define project trajectories meaningfully. As algorithms grow increasingly sophisticated, so too must our evaluative frameworks evolve responsively. Embracing diversity among available tools empowers practitioners to navigate complexity wisely, transforming abstract numbers into tangible value creation opportunities consistently.